In this video, we're going to cover suggested homework problems from 9.2. The section heading is series and convergence. Smaller topics within this section are convergence and divergence of infinite series, geometric series, telescoping series, and the nth term test for divergence. We'll also talk about partial sums and some other things as we go along. So I may need to stop and define some terms here as we go along, but hopefully you have looked at the note packet for this section and are ready to start the homework. So let's go ahead and get started with number one. To explain the difference between the statement the limit as n goes to infinity of a sub n is equal to 5. This would mean that the nth term of the series, now that we're talking about series, equals 5, or it could mean that the limit of a sequence it may mean this, or it may mean that the limit of the sequence a sub n equals 5. When we say summation from n equals 1 to infinity of a sub n equals 5, that means that a1 plus a2 plus a3 plus ... all the way out to infinity equals 5. It's exactly equal to this. This statement means that, and that statement means that. And this means the limit of the sequence of partial sums which I'll write as the sequence of S sub n is 5. I guess I should tell you what a partial sum is here. So S sub 1 is just the first term. S sub 2 is equal to the sum of the first 2 terms. S3 is equal to the sum of the first 3 terms. And so on and so forth to S sub n is the sum of the first n terms. And if we let n go to infinity, limit of S sub n as n goes to infinity, if that equals a finite number s, we say that the series converges. If limit as n goes to infinity of S sub n does not exist, the series diverges. So a series is going to be this thing that has a summation symbol. A sequence is just going to be an ordered list. You'll know the difference between them because a series is just going to have a list that's a comma separated list, whereas a sequence is going to be a comma separated list. A series is going to be a summation. It has a summation symbol or has plus or minus signs because we could be adding negative terms. I hope I said that right. It's hard to keep the words straight in here, but we talked about sequences in 9.1 so that we could talk about the sequence of partial sums here in 9.2 for the limit definition of convergence of a series. So let's go on to another important question here with number 3. Number 3 asks us about if the nth term of the series converges to 0, what can you conclude about the convergence or divergence of the series? And the answer is nothing. You can conclude nothing by knowing that the nth term goes to 0. You only know that the series diverges if the nth term is something other than 0. So the nth term test for divergence, which we'll use later, says if limit as n goes to infinity of the nth term of the series is not equal to 0, then the series diverges. This is a test for divergence. So it's the nth term test for divergence. So we can say nothing about what the series does if the nth term goes to 0, and we can only say that if the nth term, the limit of the nth term goes to something other than 0, that the series diverges. Okay, let's go ahead and look at some examples here for number 5. This is a series. Notice the plus signs here, and you may notice the pattern. We're not going to need it, but if you were to try to induce this pattern here, this is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, would go out to 1 over n squared. So this would be the sum from n equals 1 to infinity of 1 over n squared. It's going to be important that you're going to be able to do that. We're not going to need that for this particular problem. This just asks us to find the partial sums of these first 5 terms. Our calculator will be super helpful in that. So we have 1, and then we add a quarter, that's 1.25, which is the same thing as 5/4. And then actually, let me change this the other way around. Do exact answers first, and then decimal answers. Then I'm going to add a 1/9 to that, which is going to be 1.361. Repeating is what that will be. So I'll call that to 4 decimal places 1, 1. I'll call this 0, 0, and 4 decimal places. Let's see, 5/4 plus 1/9, and math, answer to fraction, 49 over 36. Then I want to add a 16th to that, and I'll get 1.4236, and change that to a fraction is 205 over 144, and I'll add a 25th to that, which is approximately 1.4636, and I'll change that to a fraction. It's 5269 over 3,600. So there's my exact answers for my partial sums, and there's my approximate answers for my partial sums. And we really can't get a good idea of what the partial sums may be going to here. That's really not important, but it does look like they are getting smaller and smaller amounts being added to them each time. There's a possibility that this is going to get closer and closer and closer to a number, like maybe 2. I don't know how much is going to be added here, but it looks like it's possible that this could go towards something. What it goes towards is not important to us right now. Just seeing if the list of partial sums blows up to infinity or looks like it's converging to a finite number. This looks like it's converging to a finite number. Let's look at number 9. N equals 1 to infinity, 3 over 2 to the n minus 1. S1 is going to be 3 over 2 to the 0 is 3 over 1 is 3. S2 is 3 over 2 to the first is 3 halves. This is 3.1234 decimal places, 1.5, 4 decimal places. S3 is 3 over 2 squared is 3/4 is 0.7500. S4 is 3 over 2 to the third is 3/8 is 0.3750. S5 is 3 over 2 to the fourth is 3/16 is 0.1875. Just check that last one. Yes, okay. So let's look now at number 11. If you want to know how I just did these in my head, each time I'm dividing by 2. So that's why I didn't need my calculator, except I checked at the end to make sure that I didn't make a mistake when I was dividing in my head. So 11. Now we want to verify convergence or verify divergence. So telling us all of these diverge, and we want to know why they diverge. So this one is a divergent geometric series. R is equal to 5/2, which is greater than 1. So my conditions for convergence of a geometric series is in the form of n equals 0 to infinity of a sub 0 times r to the n, and it converges if and only if the absolute value of r is less than 1, meaning r is between -1 and 1. It will diverge when the absolute value of r is greater than or equal to 1. Okay, so let's look at 15. N equals 1 to infinity of n cubed plus 1 over n cubed plus n squared. Let's use the nth term test for divergence. Limit as n goes to infinity, 1 plus n to the -3rd over 1 plus n to the -1st. So 1 over 1 is 1 is not equal to 0, so diverges by the nth term test for divergence. Look at number 19. Told to verify convergence here. So n equals 0 to infinity of 5, 6 to the n. This is a convergent geometric series. R is equal to 5, 6 is less than 1. Look at number 23. So yeah, so 1 over n times n plus 1, and this will be equal to n equals 1 to infinity of a over n plus b over n plus 1. And so I want a times n plus 1 plus b n over n times n plus 1 is equal to 1 over n times n plus 1. A plus b is equal to 0 because when I distribute and compare coefficients, there's 0 n's on the right. A is equal to 1. That means that 1 plus b is equal to 0 and b is equal to negative 1. So this turns into summation n equals 1 to infinity of 1 over n times n plus 1 is equal to the summation n equals 1 to infinity 1 over n minus 1 over n plus 1. Let's write out the pattern here for our nth partial sum, and Sn is going to be equal to 1 over n minus, it's going to be first term, 1 minus 1/2 plus, and then second group, 1/2 minus 1/3 plus 1/3 minus 1/4 plus dot, 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 plus 1 over n minus 1 over n minus 1. So what we're going to see is that this 1/2 is going to cancel out with that negative 1/2, and this 1/3 with that negative 1/3, and there will be a 1/4 here that cancels out with that negative 1/4, and there will be a negative 1 over n that cancels out with this 1 over n, and I'll be left with the same number of terms left and right. So one term on the left, one term on the right. My Sn is equal to 1 minus 1 over n plus 1. So my S is going to be the limit as n goes to infinity of Sn is going to be 1 minus 1 over, would be equal to the limit as n goes to infinity of 1 minus 1 over n plus 1 equals 1 minus 0 is 1. So this converges because the limit of the limit as n goes to infinity of the nth partial sum is equal to a finite number L, which is the sum of the series. So this is one of the cases where we're actually going to find the sum to prove convergence of the series. That's very rare to do that. And this is going to be one of those cases where if it tells you to find what the series converges to, then it's either going to be telescoping like this, or it's going to be geometric. So I don't think that we talked about what the sum of this geometric series was, but I'll tell you the formula for if we have n equals 0 to infinity of a sub 0, which is the first term here of the sequence times r to the n, its s is exactly equal to a sub 0 over 1 minus r. Again, the absolute value of r has to be less than 1 for that to be true. So we just have a formula here for s, where we say s is equal to a sub 0 over 1 minus r. Now, sometimes we have a geometric series that's indexed at 1, and we have here r to the n, something like this. Right? But we don't really have an A0 term. Well, what we're going to have to do is we're going to have to call this equal to the first term will be r, and then it will be times r to the n after that, and this will be r over 1, like that. It's hard to write out, but if it's written in this form here, then we go for that. I'll show you an example of it. It's not hard to rewrite them. So they'll just try and trick you and start at 1 sometimes. So in fact, I may have an example of one coming up here. Okay, find the sum of the convergence series. So here we go for number 29. Starting indexed at 0, so we get to use our formula we just talked about. Our A0 is 5, our R is 2/3, so S is equal to A0 over 1 minus R is 5 over 1/3, multiply by 3 over 3 to get rid of the denominator, and my sum is 15. 33. See if we can establish a pattern here with number 33. So this is 8 plus 6 plus 9/2 plus 27/8. So it looks like I'm multiplying by 3/4 each time, starting at 8. So this looks like n equals 0 to infinity of 8 times 3/4 to the n. And that's going to be equal to 8 over 1 minus 3/4, since 3/4 is less than 1, will be 8 over 1/4, multiplied by 4 over 4, and 8 times 4 is 32. Right. Let's look at this next one. This is the one that I was referring to that's a little bit tricky because they index it at 1. So n equals 1 to infinity of sine 1 to the n. So I'm going to have to say, well, this is really sine 1 plus sine 1 squared plus ... like that. So if I factor out sine of 1, that's 1 plus sine of 1 plus sine squared of 1 plus ... is going to be summation from n equals 0 to infinity of sine of 1 times sine of 1 to the n. So my A0 is sine of 1, and my R is equal to sine of 1. And just confirm with your calculator that sine of 1 is between 0 and 1. It is. So S is going to be sine of 1 over 1 minus sine of 1. And we can't really do anything about that, but let's just estimate it here. Sine of 1 divided by 1 minus sine of 1 is approximately 5.3080. Moving on now to number 43. I really like this type of a problem. There's a couple of different ways to solve this problem. We're going to be solving them with calculus, but there's a pre-algebra way to solve these problems that's really fun. If you want to see that, and you go to the college where I work, come in and see me for tutoring, and I'll show you the method that I learned in 8th grade. It's a lot of fun. I may have included it in the note packets as well. So first thing that I want to do though is multiply by 1000 to make this 1 over 1000 times 75.7575, and so on, right? So this is 1 over 1000 times 75 plus 75 over 100 plus 75 over, and I'll call this 10 squared. I'll call this 10 to the 4th. I'll call this 75 over 10 to the 6th plus dot, dot, dot in that pattern because we keep moving in groups of 2 here. So I'm going to pull the 75 out as part of the common factor over 1000. And this is going to be 1 plus 10 to the negative 2nd plus 10 to the negative 4th plus 10 to the negative 6th plus dot, dot, dot. So 25 goes into 75 3 times, 25 goes into 1000 40 times, and then this is summation. I'll put this on the inside here, 3 over 40 times summation of 10 to the negative 2nd to the n, or 1 over 100 to the n. So there's part A, is to write the repeating decimal as a geometric series. And then part B is to use our formula for S to write this as a rational number. So we have 3 over 40 over 1 minus 1 over 100. So I'm going to write that as 3 over 40 divided by 99 over 100 is 3 over 40 times 100 over 99. So I'm going to do some simplification here. So this is 3 goes into 99 33 times. Going to take out the 10 here. So far this is 100 over, or I'm sorry, 10 over 4 times 33. 2 goes into 4 2 times, and then to 10 5 times. So this simplifies to be 5 over 66. Now, yeah, let me go ahead and show you the other way. So it comes out to be relatively the same thing. So if I have 0.075 repeating, and I'm going to call that x, this is my pre-algebra way. This is not the calculus way, so don't do it this way unless the teacher tells you to. Then if I take 1000 times x, I get 75.757575 dot, 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 right? So if I have 10x, that's going to be 0.757575 dot, dot, dot. And I'm going to subtract 10x from 1000x to get 990x, and that's going to be 75. So x is going to be 75 over 990, and then we can reduce the fraction here. That 5 goes into 75 15 times, and then 1 9 8, and then this is divisible by 3 5 and 66, and there we go. There's our final answer. We get 5 over 66 both ways. So pre-algebra technique to try and get the repeating decimals to line up and subtract them off by multiplying by powers of 10 and sliding the decimal around until you get the repeating parts to line up and cancel each other out. Algebra or calculus 2 method is to write it as a geometric series and use your geometric sum. All right, let's look at number 49. Summation n equals 1 to infinity, 1 over n minus 1 over n plus 2 is going to be, let's find that partial sum. It'll be 1 minus a third plus a half minus a fourth plus a third minus a fifth plus, and then dot, 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 plus, and I'll need two sets of parentheses here. This is 1 over n minus 1 over n plus 2, being minus 1 over n plus 1, and this is 1 over n minus 1 because this 1/3 doesn't cancel out until the third group of parentheses. So there's a 1/4 that will cancel out with this 1/4 that's up here, and a 1/5 that will cancel out with a 1/5 that's somewhere up here, and so on. And I have two terms on the left-hand side, so I'll be left with two terms on the right-hand side to match up with them, and my Sn is going to be 1 plus 1/2 minus 1 over n plus 1 minus 1 over n plus 2. So my S is going to be the limit as n goes to infinity of 1 plus a half minus 1 over n plus 1 minus 1 over n plus 2 is equal to 1 plus a half is 3/2. The other ones go to 0. And it converges. So let's look at number 51. 51 says summation from n equals 1 to infinity, 3 to the n over n cubed. So let's try and look at the nth term test here and see what's happening. Okay, so this is approaching infinity over infinity, so I use L'Hopital's rule, and this is going to be limit as n goes to infinity of 3n squared, and this is going to be ln of 3 times 3 to the n, and this is still going to go to infinity over infinity, so I'll use L'Hopital's rule again, and this is ln of 3 squared times 3 to the n over 6n, which still goes to infinity over infinity, so I'll use L'Hopital's rule again. And this is going to be ln of 3 to the third times 3 to the n over 6. And that's going to go to infinity, and it diverges. Now, we could have just done that in one step by saying that we know that the exponential function here grows faster than this power function here, this third degree polynomial. The exponential functions grow faster than any power function, and that since the faster growing function is on top, it's going to go to infinity and diverge. If the faster growing function is on the bottom, it's going to go towards 0 and it's going to converge. So that's an important concept here, so you don't have to use L'Hopital's rule over and over and over again. Let's look at 57, which is n equals 1 to infinity of arc tangent of n. Let's do the nth term test here. And that's going to be equal to pi over 2. Remember, the arc tangent approaches a horizontal asymptote on the right of pi over 2 and a horizontal asymptote on the left of negative pi over 2. and that's not equal to 0, so it diverges by the nth term test for divergence. '63. Told to make the series converge. This is going to be more like what we're going to do at the end of this chapter. We're going to have something called power series, and they're going to look like this, and we're going to test for what's called the interval of convergence. But for right now, we can rewrite this as n equals 0 to infinity of x minus 1 times x minus 1 to the n. And so that'll be geometric in the right form. And as long as the absolute value of x minus 1 is less than 1, so x minus 1 is between -1 and 1, I'll add 1 to everything. So as long as x is between 0 and 2, then s will be equal to my first term over 1 minus my ratio here, the x minus 1 over 1 minus x plus 1 is x minus 1 over 2 minus x. So watch out for your limit here to make this geometric, and this sum is only good when x is between 0 and 2. And I can tell you that it's not going to be good for either 0 or 2. We'll learn how to test the endpoints later, but we know that it's good between 0 and 2 for our x values. All right, let's look at number 75. Distance a ball is dropped from a height of 16 feet. Let's draw a picture here. So we have the ball falls 16 feet first, and then hits the ground, and it goes back up to 81% of its original height, and then comes back down, and then 81% of that height, and comes back down, and so on and so forth, right? And then it goes up, down, for the rest of its path. But it only came down the first time, right? So there's a couple different ways that you could write this, but I'm going to say that this is going to be 16 plus the summation from n equals 1 to infinity of 81% to the n of 32. And how did I get that? Well, it is looking at this as 16 plus 2 times 0.81 times 16 plus 2 times 0.81 squared times, so this is 81% of that number right there. So there it is. And then so on and so forth. So I multiplied this 2 in there with the 16 to get 16 plus 81% of 32 plus 0.81 squared times 32 plus so on and so forth. And this starts at 1. So what I'm going to do is I'm going to pull this, take 81% of 32, and that's 25.92 times 0.81 to the n, and write that as starting at n equals 0, so that I can use my formula. 16 plus 25.92 over 1 minus 0.81. So divided by 1 minus 0.81, or you could just divide by 0.19, and then plus 16. And this is going to be approximately 152.42 feet that the ball is going to travel on its entire path, starting from the 16-foot tall height and going down, up, down, up, down, up, down until it stops. All right, let's look at this last problem here for this video, problem number 81. This one's quite interesting to me. Kind of hard to draw, but we'll take a look at it. So we start off with this square that is 16 by 16. And I just want to note as we start off here that 16 times 16 is 256. Hold this number, area of the original square is 256 square inches. Just hold that for later. So now if we take the midpoints of the sides and connect them like so, so we have a new square where these sides are 8 here that were the bisected portions here. This is a 45, 45, 90 right triangle. So the sides of this square that is formed here have sides of 8 root 2. So now I want to talk about the area of these upper triangles right here and add them together. So I have 2 times 1/2 times my base times my height for these 2 portions right here, and the 2 and the 1/2 cancel each other out, and I get 64. So that's my first step. Now I want to do this again and find the midpoints. And don't worry, those 8 root 2's will be important in just a second. So I'm going to make another square in here. And it's going to be half of 8 root 2 on each side is going to be, these sides are 4 root 2 and 4 root 2. So this side is going to be root 2 times that. This side is going to be is going to be 8 in here. So this is 8, and I want, it doesn't matter which 2, but I'm going to take these see if I kind of turn it on its side here, I want the ones that, let's say, are this one and this one. I'm going to try to always take the same two pieces. So that's going to be 4 root 2 times 4 root 2 times 2 times a half, and that's going to be 16 times 2 is 32. And I'll take one more step so you can see that each time I'm cutting this in half. And so this would be 4 and 4 here. So this would be so this would be 4 root 2 for this diagonal. And then I would have 2 times 1/2 times 4 times 4 is going to be 16. So just induce the pattern here every time I'm cutting it in half. So, and when this process is continued 5 more times, so I want 6 times total. So 1, 2, 3, 4, 5, and 6 times here. Let's add it together. 64 plus 32 plus 16 plus 8 plus 4 plus 2 is going to be 126 times. So now I want to figure out a infinite series to go ahead and find the total area of this idea where I keep taking half each time and adding it together. And that would be summation n equals 0 to infinity of 64 is my base number times 1/2 to the n. So that's going to be equal to 64 over 1 minus 1/2 is going to be equal to 64 over 1/2 is 128. And you might have figured this out. These are square inches, by the way. Look at how close that's getting already just by only going 6 iterations here. We're getting really close to what the actual sum is, but you might have guessed because we're taking 2 of the 4 triangles that are formed from this, that we should be getting half of the total area, and that the total area was 256, and half of 256 is 128. So that's why I said, note that 256. We'll come back and we'll use that here to say that we expected it to be half of the area, and it is half of the area of the 16 by 16 square. All right, that is it for this video. We'll come back next time and we'll talk about suggested homework problems from 9.3. And we'll be talking about p-series and the integral test. So see you for the next video.